All right. Thanks for reminding me. So the book chapters are Hagan et al. And they're going to be chapters 8 and 9. And that will be representative of the topics of today, and possibly it could spill over to next class. Okay, so so we are talking about, basically the goal is to kind of talk about optimization. That's kind of optimization of functions, right? That's the high level goal. And I want to spend a few minutes talking about why this is really important. In some sense, optimization for neural networks is almost a really big percentage of what you need to do to have a successful neural network, right? So if you recall from the RBF class, right, at the end, finally, we formulated this as this minimization problem, right? So basically, we are trying to find the matrix W such that this function is minimized, and that is exactly an optimization problem. And then we see that W is a parameter in this function, and this represents the weight of this network. And after a lot of manipulation, we finally found a closed form solution for this matrix. And that way we are kind of in one shot learning the matrices, the weight matrices, or the values of the weights. We will not always be that lucky. It's not always going to be easy to find a closed form expression like this. In that case, we need what we are called numerical methods, or kind of iterative methods, which is what we are going to kind of try to learn today. The other thing that you note is that we also rely a lot on taking differentiation of functions with respect to parameters, and what is known as gradients. So we need to kind of understand those well. And as part of this, we would kind of understand how we take a derivative of a scalar with respect to a matrix, or derivative of a vector with respect to another vector. We'll understand these concepts and make sure that we are all on the same page. Okay. So coming back to optimization, like I'm going to make a few statements which I probably made before. Like one of the most important algorithms in neural networks is backpropagation. Propagation, which is what we used to train multi-layer perceptrons, or like deep neural networks, right? And let's kind of abbreviate this as BP. Okay. One statement I'll make is BP is basically stochastic gradient descent plus the chain rule from calculus, right? So when the backpropagation algorithm was discovered, originally it wasn't known that this is a kind of an instantiation of the stochastic gradient descent algorithm, but later on it was discovered. And then you have the chain rule to kind of like, that's what you do in the backward pass, which we will look starting next class, or possibly next class, that backpropagation is a combination of these two ingredients. So understanding gradient descent, which is the one of the most well-known optimization techniques in used in machine learning, is going to be crucial. So we need to really understand optimization well, right? And when we are optimizing, what are we talking about? So let's start looking at some examples. Okay. Draw. Okay. So let's actually kind of think about the perceptron algorithm. And the we saw that the learning rule looks something like this, right? So either it's W equal to W plus X, or the other way is W equal to W minus X, right? And we basically we gave an intuition of these rules, like how this rule helps us to kind of make sure that the inner product within the weight vector and the input vector is has the right uh, sign, right? So if it's the label is positive and the dot product is negative, we try to increase it by adding x to the weight vector and vice versa, right? But this actually also is an instantiation of the stochastic gradient descent rule. And how can we see that? So let's think about this. So when we in universally in machine learning, the way we think about optimization is we first define a loss function, right? So let's say we have kind of a classification problem like this, right? Where we're kind of trying to find this boundary, right? And then we define a loss function by thinking of, if we are trying to classify this into two classes, and if you have some points like here we have a misclassified point, or here we misclassified point, we try to see in some sense what is the error of these, right? So that's one example. Another example could be basically just a function approximation, right? So let's say you kind of have a bunch of points, right? Right. So we have a kind of a output variable y and an input variable x. And let's say we say that this is going to be my regression line. And then we try to see whether this is a good fit by trying to find some sort of distance from every point to this line, right? Which is my which is my model. And this line is going to be parameters by, in this case, we can just have two parameters like w and x. So this would be a line would be like probably wx plus b, which is the equation of this line. And then we also have an actual y value, right, which is these points. So I have y, and then if I take the difference, that gives me an idea of the error that I've made by thinking of this as my model, right? And then what we typically would do is that, let's say it's going to be easier if you think of a quadratic function. So let's square this and make this my loss, right? And now in this case, my y and x are my given data. So in terms of this optimization problem, we can think of this as the constant data set. The only thing that is varying is this w and b. So I have a function of w and b, right? And then my goal is to kind of find the best values of w and b such that this loss is minimized. Because if this loss is minimized, that means I have a very good fitting line here. Okay. And then what would we do? We would basically take to kind of find the best points, we take the derivative of this loss function with respect to w. In this case, it will going to be 2 times w minus y minus w x plus b. And then with respect to w, then we're going to have a minus x. And then with respect to b, we're going to have by b, and this should be 2 times y minus w x. This should actually be a minus. and then this will have a -1. Okay. And now what do we do to find the best values of W and B? Again, we're just gonna set these to 0, right? And then these two terms, we can take them together, right? Put them together in a vector form, and this is what we would call the gradient. This is going to be the gradient of this loss function with respect to the parameters W and B. And we want to set this to 0 because we know that when we have a minima, so if this is a function, right, and then you can see that the point where it is minimum, I look at the slope, and the slope is 0, right, which is the main idea of optimization. So in 1D, it's a single quantity, but in higher dimensions, it's going to be a vector of partial derivatives, which is what we know as the gradient of a function. We set this to 0, which means each of these components has to be 0. So both of these are going to be 0. And in this simple case, you can probably solve this. You can kind of see that this could be yx minus, yes, this is going to be minus minus wx square minus bx will be 0. And in the second case, you have the equation y minus wx minus b equal to 0. And now we can write this as, so actually we can formulate this as, we have minus x square, so minus x square, right? And then minus x, and then I think it's going minus x, right? So this is going to be for, let's see. So this loss function, actually, you're going to have to do a summation over multiple data points, right? So everywhere you're going to have xi, yi, and then you're going to have a summation here, xi, yi, and also a summation here, because you have many data points and many equations, right? And then I think this we can erase, but you can kind of continue this and you will find an expression for the weight and the b values, right? So that's basically the idea of optimization. Any questions at this point? Okay, so let's kind of think about the perceptron. So the main kind of way of thinking about machine learning is kind of coming up with a good loss function, right? So if you think about the perceptron, we can also formulate a possible loss function, right? So we can think of a loss function for the perceptron as the loss of a weight vector, right? Is for any given point x and y in perceptron, right? We can think of y as the label, right? So let's say y can be +1 or -1. So it can be in these two classes, right? And then we can think of a possible loss function is, let's take W transpose X and then subtract Y and then take the square of this. And the idea is that if Y is a positive label, then we expect this to be high, right? And then if Y is a negative value, we expect this to be negative. And then by trying to minimize this, you're trying to minimize the distance between your computed value, which is this one, and Y, right? So this would be this might not be the best loss function. This is a possible loss function. But if you think about this, now let's take the gradient of L with respect to W, and let's put a half here. And then now if I take the gradient of this, what I'm going to get is going to be W transpose X minus Y. And then I have to take the derivative of this part with respect to W, which is going to be just X. Okay, because the dot product, if you take the dot product and the derivative with respect to W, you're just going to get back the X. Okay, and now we're going to talk later about gradient descent. So the gradient descent rule is that the new value of the weight vector is basically the old value minus some learning rate times the gradient. Okay, and I will explain this, but this is basically the gradient descent. This is gradient descent equation, and this is the most important equation in optimization for machine learning. So gradient descent. Okay, and now let's plug in those values here. So if it's W old minus eta times this value, X, right? And now what is this? Like, this is kind of a representation of the error of the perceptron, right? And then kind of in some sense the difference in your weight is basically minus times the error function times X, right? So you can see that this is kind of similar to the perceptron rule, is that if you actually make an error, right, which is what we say, that if W transpose X is positive and Y is negative or -1, that would mean an error. And then if you have an error, you kind of change the weight proportional to X, right? So that kind of should remind you of the perceptron rule. But again, it also kind of boils down to a formal optimization method. Okay. All right. Cool. Uh, any questions so far? Okay. So So in general, any machine learning problem or kind of weight, uh, the problem of learning the weights, you can cast as some type of loss function of your weight parameters, and then you want to minimize the weights, and then the optimal values of the weights would give you your network parameters, right? So that's going to be the form of most machine learning formulations, right? And in some cases, we are going to get closed form solutions like in the radial basis function. But in most other cases, we are going to have to use an iterative method similar to gradient descent, right? So that's going to be the workforce, the most powerful method in machine learning. Okay. So now let's start talking about some basics of calculus that we need for this course, right? So, and in calculus, we have two parts. We have differentiation and integration. What we mostly need in machine learning is differentiation, especially differentiation of vector valued functions, right? So we know that when we have a function which is from R to R, right? Then we know how to compute the derivative in general, right? Okay. Now there are things get more interesting when we have uh, functions like this. So let's say we have a function from a d-dimensional space to a scalar value, right? So an input to this function is actually a vector, right? In this case, it's a d-dimensional vector. And we get back just a real number. Okay. In this case, what is the differential object? The object in this case is known as the gradient. Okay. And this is computed as basically we take the derivative, partial derivative of the function with respect to every input parameter, right? Sorry. Okay. And then this, what type of object is this? Can anyone tell me?
Matrix.
It's a matrix, but in this case, it's a column vector,
Yeah.
right? And it also lives in the space RD, right? So if we have a function from a vector to a scalar, then the gradient of that function is also going to be a vector, right? So that's one thing I wanted to mention here. Okay. And this is a very important object, as you will see. This is known as the gradient of the function. Okay. So let's see if you can find an example. Okay, so let's look at it just to give an example. So let's say I have a function of w, and w is basically, it has three parameters, w1, w2, and w3, and my function is 3 w1 w2 plus w3, and now I want to compute the gradient of this function. So what do I do? My first entry is the derivative of this function with respect to what? As we said that this lives in, let's say, R3. So the gradient will also be a three-dimensional object, so we will have three derivatives, right? So what will be the first entry? Anyone?
Double W1.
Yes, it's going to be derivative with respect to W1, and the second will be the derivative with respect to W2, and the third one will be the derivative with respect to W3. Okay. And now let's try to compute them. So we have this function here. What is the derivative of this function with respect to W1? Anyone want to try?
3W2.
3W2, right? Because W3 is considered constant with respect to W1. W2 is a constant with respect to W1. So the part, this is the parameter W1. So we just take 3 and W2. So it's going to be 3W2. Very good. And then what is the derivative with respect to W2?
3W1.
3W1, yes. And then finally, with respect to W3, what should we get?
1.
1. Yeah, exactly. Okay, very good. Okay. All right. Let's look at a few more examples because this gradient is a very important concept. So let's say, and this would be a familiar function. Let's say we have a weight vector which lives in d-dimensional space, right? And then our function is basically a dot product. Okay, so it's going to be W transpose X, where you can think of X as some sort of input vector, just like in perceptron. And now we want to compute the gradient of this function with respect to W. Okay, and here is where you can start thinking about, like, the trick that we did last time is that we think of these as scalars. So if this was a scalar instead of a vector, what would be the derivative of this function with respect to W? If both W and X were scalars and W and X is a constant? So if you have a function of, let's say, t equal to at, then what is df x? Okay, yes, I see in the chat. Very good. That is exactly correct. So what I was trying to say here is that this is going to be a, and this would also be x. But we want to actually do this properly. So if this is a dot product, we know that we can write it as w1 x1 plus w2 x2 plus dot 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 plus W D X D. And now we just need to take the derivative of this with respect to each parameter. So what is going to be W1? If it's W1, then everything else is constant, and we just take X1. That's the only value here, right? And then if you do WF by W2, it should be X2, and so on for all the parameters. So that means that your gradient is basically going to be, you just stack together all the values, which are now X1, X2, XD, and you put them together, and that turns out to be exactly to be the input X vector. Okay, so that works out perfectly. Okay, all right. So with this example, I hope this is clear to everyone. This is a simple example. Before I do another example, I want to kind of introduce some more ideas. Actually, let's do another example and then we'll go there. So another important function that you'll see a lot is this function. It's the norm function. Okay, I take the norm of this weight vector, right? So W is going to be in d-dimensional space, right? And again, if you think about comparing with a scalar case, if W was a scalar, this would just be a W square function. In that case, what would be the derivative of W square with respect to W? Is anyone in the chat gonna say? So it would be twice W, right? And we'll see that in the norm case, for where W is a vector, we're gonna get the exact same answer, right? But just W is gonna be a high dimensional object. So if this is W norm square, and W is basically a based, W has these components, right? W1 to WD. What is a expression for the norm square of W? Can anyone tell me?
W transpose times W.
Yep, that's correct. W transpose times W. And then if you expand it out, what do you get? If you actually calculate the dot product, this is going to be a row vector, and then you have the column vector. And now if you actually take the dot product, what do you get?
W1 square plus W2 square to WD square.
Exactly. And now in this form, you can see that if I take the partial derivative of f with respect to the jth component, what will I get? So j runs from 1 to d, right? If I take any one of these, like let's say W2, the derivative with respect to W2 is going to be, the only term that's going to survive is W2 square, and everything else is going to be 0. And then you take the derivative of that, you get twice W2. So if I take with respect to Wj, then this should be 2 times Wj, right? Hope this is clear. And then if you put them together in a gradient, what do you get? You get twice W1 twice W2 twice WD, and then this is just basically 2 times the W vector, right? So again, this works out nicely. All right. Okay. So far, so good. Everything clear? So the gradient is going to be a very important object for us. Okay. So now let's talk about another important idea from calculus, which is the Taylor series. And this is going to be really crucial for us to understand optimization. Okay. So the Taylor series is basically like this. So you have a function, right? And you're trying to compute the value of the function at the vicinity of a given value x. So you take a small step in some direction of x, right? And let's initially think of x being a single real number, and then function of x is also a real number, so it's a scalar function. The way we can approximate this is using the Taylor series. So this is how it looks. We first have f of x. I hope everyone is more or less familiar with Taylor series, right? What would be the next term? Anyone can guess, or anyone knows the next term of this Taylor series expansion?
Isn't it like 1.5 times the second derivative?
That's a good thing you said, but that's going to be the third term. So basically, we're going to have terms proportional to the powers of this increment delta x. So if this one is proportional to the power, the 0th power of delta x, the second one is going to be delta x time the first derivative of x. Okay, and this is always the first approximation of a function, right? And now, even if you don't add any terms, you just look what happens here. If I just think of this, I take f of x plus delta x, right? And then I take fx on this side, and then subtract by delta x. And we know that delta x is a small number, and this is basically f dash of x, right? Which is the derivative of x, and that's the formula for derivative that we usually know, right? But it comes from the Taylor series. Okay, and the next term is going to be now 1/2, which is what Onum said. This will be proportional to the square of the difference delta x. And then what will we what would we add here? We add the second derivative of x. Okay, and there are other higher order terms which are negligible if delta x is small, but this is the usual approximation that we think about. And now let's kind of look at this and see what we need to change if now x is going to be a d-dimensional vector. Okay, and then f is a function from the d-dimensional vector space to just a scalar in this case. Okay, and now let's try to work out the Taylor series for this. Okay, so what is it going to be? It's going to be, again, x is a vector. So what type of object is delta x in this case? Like, where does it live? When x is a d-dimensional vector, what is delta x?
Also a d-dimensional vector?
Exactly, it's also d-dimensional vector. It's just the difference between two x's, right? Where two x's that are nearby, so the difference is also small, right? So this is also a vector, so we can add these two vectors and look at the function value at that aggregate vector. So now we're going to just look at this and try to replace with corresponding terms that make sense, right? So the first thing is f of x, which we can just write here. There is nothing to change here. This is just the value of f of x. And now what about this term? When x is a vector, what can we use here? So first we have delta x, right? So delta x is a vector, and then we can, what do we use instead of f dash of x? What object can we use here?
Gradient?
The gradient, exactly. So the gradient of f, right? And now we multiply these two. So this is a vector and this is a vector. And now let's look at the dimensionality. F of x is a real number and this is also a real number. So I need this to be a real number. So how can I take two vectors and get a real number?
Is it the dot product?
Exactly. We just do the dot product. And that way everything makes sense. Very good. Okay, very good. And now let's look at the next term. So the next term I have 1 by 2, right? And now when I have, basically this is kind of, you can think of this as x squared, an x squared term. When x is a vector, what is the corresponding square term that you can think about? So if you have a vector and you want to kind of think of squaring it, what would you do? You can look at some hints over here, right? Maybe this could give you a hint, or this, right? So if you take a vector and take a inner product with itself, or a dot product, then you can get something like a square, right? So we can do something similar like that. So we can think of delta x transpose, and there's going to be a delta x. Okay, but that's not enough, right? Because we also need to something to replace this term here. Okay, so what can we do here? So let's think about this. So how do we generalize this object, the second derivative? Okay, so we know that the first derivative is a vector, right? And what was this value? This was delta f by delta x1. And just for simplicity, let's just use 2D vectors. So this is delta f by delta x2. Okay, so this is my gradient, or the first order derivative of this vector, of this function. So now if I want to take the second derivative of this object, what can we do? So that was going to be defined by this thing, right? So the way we define it is that we take this first object and we differentiate again with respect to x1 and x2, and we put it in the first row, right? So if I take this and differentiate again with respect to x1, I get del square f with respect to del x1 square. And then I take this object, right, and differentiate with respect to x2. Then what do I get? I get del square f with respect to, again, del x2 del x1. Okay. And now let's take the second component here and I differentiate this with respect to x1, then I'm gonna get del square f divided by del x1 del x2, and finally this last term is going to be del square f with respect to del x2 square. And now I put everything together. And now what type of object is this? This is now a 2 by 2 matrix, right? And the rules of calculus say that this is going to be true, that if I take with respect to x1 and x2, this is going to be the same as which means that these off-diagonal terms are equal. And what does this tell us about this matrix del square f? If the terms of the diagonal are always matching each other, what is the property of that matrix?
Symmetrical.
It's symmetric, right? So this is going to be a symmetric matrix. Very good. Okay, so this matrix is called the Hessian matrix, which is the matrix of all possible second order derivatives. All right. Okay. So now the Hessian in general is going to be a D by D matrix. And this is going to be the representative of the second derivative here. So now somehow I need to put this in this equation. So I can just put it here, right? And then can anyone tell me what this object is called? What type of object is this?
Matrix.
It's a matrix, but we have basically a vector transpose times a matrix times a vector. What do we
Is it
call this?
is this pseudo inverse?
No, this is a quadratic form, right? So it's like this, x transpose A and X. That's a quadratic form. Okay, and we'll see that it's gonna play a very important role. Okay, so this is a very important formula for us. So this is the Taylor expansion for a vector valued function. Okay. All right. Okay. All right. So let's talk about a few more things. I want to, this is another thing that's going to be very important, which is called a directional derivative. Okay. And basically it's defined like this. So let's say I have a vector x in Rd, right? And so X is a vector in RD, right? Which means this is a vector in RD, and there are many ways in which I can extend X. Like X can move in a lot of directions. So there are many directions in which I can take a derivative. So let's think about this. If I have a 1D function, right? When we think about taking the derivative, what are we doing? We are basically thinking of, if this is a value of X, we can only move X in this direction or this direction, right? If I have a 2D function, right? If this is a 2D function where I have two parameters, and then let's say X is a point here, then I can change X1 and X2 where I move a little bit in this direction. I can move in this direction. I can move in this direction. I have a lot of possibilities, right? I can move in this direction. So the direction derivative says that if I have a vector X such as this, I want to choose a particular direction D and move a bit in that direction. And I want to see how the function changes, right? So the way I think about this is I have function, right? And I am currently at X, and I move in the direction of D a small amount alpha, where alpha is a small value. And then I see how much I change with respect to where I originally was, right? And then I divide this by alpha, and I take the limit of alpha goes to 0. And this is called, we can call this as the derivative of X in the direction of alpha. And this is the directional derivative of the function f. Okay, and as it turns out, this will always turn out to be the inner product of the direction d and the gradient of the function f. Okay, so this is a very important result, and let's look at an example of this. And with this, we're going to actually see that there is another way of finding derivatives of vector valued functions. So let's revisit some of the functions. So let's look at this function, which was W transpose X, right? So let's compute the directional derivative of this function. So it's going to be limit alpha tends to 0. So I am going to take X plus alpha D. Okay, that's the value of at X plus alpha D. I'm going to subtract the value of at X, which is W transpose X, and we divide it by alpha, right? And you see this term W transpose X and W transpose X are the same, so this is going to go away. And the remaining term is going to be alpha times W transpose D, and I have an alpha back here, and then this alpha and alpha go away. And then what I'm left with is the direction D inner product with the value W. And then according to this formula, this means that I actually have that the derivative, the gradient of f of x is actually going to be equal to W. And that is exactly what we expect. Okay. Is this making sense? This is a very important concept, and you'll see a lot of use of this. Any questions on this so far? Okay. Yeah. Okay. So no questions. All right. Good. All right. So now let's look at this our new tool, which is a directional derivative, and use it to compute a more complex derivative, which is now we're going to take the derivative of a quadratic form. Why? And why do we want to do that? Because we see here in the Taylor expansion, we have this quadratic term. So I want to be able to take the derivative of this quadratic term with respect to x and see what I get. Okay. So let's consider this term 1/2 x transpose a x, where I'm going to say that A is going to be a symmetric matrix. I want A to be symmetric, and then x is going to be a d-dimensional vector. Okay. So what is the dimension of x? Or what is the dimension of A here? Anyone? Just making sure everyone is awake. If x is RD, what has to be the dimension of A? First of all, is A a square matrix or not?
Yes.
A has to be square, and it has to also be d by d. Okay, so now I want to take the derivative. I want to find the gradient of f. Okay, what is your guess of the gradient of f?
A.
X times.
X times A, but to match the dimension I have to be A by X, right? That's so, and that's exactly correct. But now we're going to see that we're going to use the direction derivative to kind of formally find this value, right? The way we've done this in the past is that we cheated, right? We said that, let's say that x, a, and x are all scalars. In that case, it's going to be 1/2 a x squared, because for scalars it doesn't matter. And then if I take the derivative of this, then I'm just going to get ax, right? But that was just because we downgraded them to scalars, then did the scalar calculus, and then upgraded them to matrices and vectors to see that the dimensions match. But now we're going to see, using the direction derivative, we can actually derive this in a much more rigorous manner. Not fully rigorous, but still semi-rigorous. And we're going to take advantage of this thing, is that if I take the directional derivative, the directional derivative is always going to be the inner product between that direction in which we are taking this derivative and the gradient. Okay, so now let's try this on this case. So now let's take the directional derivative. It's going to be f of x plus, we choose a direction, let's say alpha t, minus f of x, and we're going to divide it by alpha, and we're going to take limit alpha goes to 0. So now let's do this. What will this be? So let's keep the 1/2 here, and then let's do this. We have x plus alpha d transpose matrix A d minus, I have x transpose x, and I have alpha below, and this is all limit alpha goes to 0, but we'll put that later. So I have 1 by twice alpha, and now let's break this down. The first term here is x transpose ax, and then I have x transpose ax, so this should go away. So let's just cancel this. And now the second term is alpha d transpose, so it's going to be alpha is a scalar, so alpha D transpose A and this X. And then I have another term alpha, which is X A alpha D. So alpha goes in the front. It's going to be X transpose A D. And the last term is this alpha D transpose A alpha D. So that's going to be a quadratic term in alpha. So alpha square D transpose A D. Okay. And now let's see what we get. So I have 1 by 2. This alpha and alpha cancel, this alpha and alpha cancel, and this alpha and alpha square cancel to get alpha. So the first term here is D inner product with a X. Okay. What about the next term? Here A is symmetric, so I can put a transpose here. And then this I can write as A X transpose times D. So this whole thing becomes A X inner product with D plus alpha times D transpose A D. And remember, we have a limit here, which is this term is limit alpha goes to 0. And if alpha goes to 0, then this term vanishes because it has an alpha here. But these two terms survive. And then we know that the inner product is symmetric, so this term and this term are actually the same. So we have 2 times D inner product with AX divided by 2. So that's the result, which is D comma AX. And now from this, can you read off the gradient of the function? What would be the gradient of the function? So this is the directional derivative of f at direction D. So what would be the gradient of the function based on this expression? Anyone? So let's compare here. For this case, right, we took the directional derivative and we found it to be the direction inner product with W, and W was the gradient. Okay. And now the function is 1/2 x transpose AX. We took the directional derivative and we found that that's equal to the direction inner product with this value AX. So what is going to be the gradient of the function?
EX.
AX, exactly. And that matches what we had expected, right? Very good. All right. Okay. Now, okay. So now let's talk about function minimization. So if you have a function, right? Typically we think about minimization, and maximization is always going to be equivalent, because if you minimize a function, if you have a maximization problem, right? If you minimize minus f, and then you take the minus, you get the maximization. So any maximization problem can be cast as a minimization problem. So we just think about minimization. If I have something like this, right, we know that the minimum is at this point, right? So this is the minimum point. Okay. So this is called a minimum point. And now we can also have a function like this. So you can have a function like this. Right? In this case, what is the minimum of this function? It's going to be at this point, right? So this is called a global minima. Okay. But let's say I was somehow here at this point, and I see that if I go in this direction, I can reach a smaller value. And I keep going, and then I reach this point, and here I see that actually my slope is 0, but this is a locally in this region, right? In this local region, this is actually the smallest point, but it's not smaller than this global minima, right? So this is what we call a local minima. Okay. So that's an important idea, because when we are optimization function using iterative methods, we might start here and we can converge to this point, but it's going to be hard for us to kind of jump back and converge to a global minima, right? So we need to understand the difference between local and global minima. Okay. So what about this case? In this case, this is a local minima, but what about the global minima for this function? Where is the global minima? Is the global minima, the global minima is actually same as the local minima, right? And that happens because this has this particular bowl-shaped structure where what we call this is actually what we know as a convex function. And if functions are convex, then local minimas are equal to global minima, which is a nice property of a convex function. And we'll define convex functions in a bit. Okay. All right. Hopefully this is like everyone has some idea of this, and this is clear. Any questions about this notion of minima and global and local minima? Any confusion about this? Okay. So what is the criteria for local minimization, for a local minima? Let's try to understand that. Okay, so let's say I have a point x, right? And I compute a function at f of x. And then I move slightly away from x at x plus delta x. So x is kind of moving a small amount. So let's say x is this point, right? And I'm moving a small amount at here, which is x plus delta x. If I want x to be a local minima, what should be the relation between f of x and f of x plus delta x, where x plus delta x is very close to x? Which one should be bigger, do you think?
X plus delta x is bigger.
Exactly, because I want x to be the minima, which means that f of x should be smallest in this local area. So if you move slightly away from x, f should only increase, right? So this should be the criteria. Very good. Okay, so now using this idea, let's try to use the Taylor expansion to kind of characterize these conditions for minima. What we are trying to do is we are trying to discover how do we characterize a local minimum of a function? Like what is the equation to characterize that? Okay, so let's look here. Let's look at the Taylor expansion that we had earlier, which is x plus delta x, which is, you know, that's f of x. And let's only keep the first approximation, which is the gradient approximation. Delta f at x. Okay, and now we said that f of x plus delta x must be greater than f of x, right? So if we apply it here, then I have that which is equal to x plus delta x dot product with the gradient, right? This must be greater or equal to f of x, and now I can get rid of this and this, and from here I have delta x transpose gradient must be greater or equal to 0. Okay, and now here's a trick that we can apply. So this condition must be true for any delta x, right? In x is a r dimension n d-dimensional vector, and delta x can be any quantity. It can be positive, negative, it can be any direction that I want to move. In particular, I can choose delta x to be the negative of this value. I can choose it to be the negative of del f of x. Is this a valid choice? Do the dimensions match up? They do, right? Because delta x is also in RD, and we know that the gradient is also a d-dimensional vector. So this is a valid choice. But now let's see if I put this into this relation here, what do I get? I get minus delta f transpose delta f is greater or equal to 0. And this term, we know this is the norm of delta f squared, and I have a minus here, so this has to be less than or equal to 0. Okay. Okay, so now we have a norm square less than or equal to 0. What does this tell us? What can we infer from here? Can we have the norm to be negative? Can it be strictly less than 0?
It has to be equal to 0 because
Exactly. Exactly. Because there are no other choices, because it cannot be negative because this is a norm. So that means that this norm squared has to be 0. And we know the property of a norm is that the only vector with 0 norm is the 0 vector. So that means that the gradient of f must itself be 0. Right? So now what we have is we have the first order property of minimization, which means that for a function to have a local minima, at that local minima the gradient must disappear. Okay, So f has a minima, let's say at point x, that implies that the gradient of f at x must be 0. Okay, so that's the first order condition for minimization. And that's why anytime we try to optimize, so if you look back here, we did some optimization practices, right? We took the derivative in this case, right? Del L by del W, and we are trying to set it to 0 because we know that at the optimum point of this loss function, these gradients must vanish, which is exactly why we did that, right? And that's kind of, we also did that in the RBF network. Okay. So now del Fx has to be 0. So now if you plug in this into our Taylor series, then this term is vanishing and then we only have this term left, right? So now let's do that. Let's now look at the second order term, and that would give us the second order condition for minimization. So now we have f of x plus delta x is f of x plus one half delta x transpose the Hessian delta x. And now we apply the same thing. We say that if x needs to be a local minima, if I perturb x by moving into a slight direction x plus delta x, then the f only can increase, which means this whole term must be greater or equal to f of x. And then if you kind of cross out this and this, you have that this term must be positive. Okay. And now let's look at this term. What does this tell us about the matrix H? We know that H is symmetric by definition. If we have that, if this is true for all del x, what does this tell about this matrix H?
Positive definite.
Positive semi-definite, exactly. So that means that H must be positive semi-definite. So that's the second order condition. And we can also write this as H. The other way to write this as H must be equal to 0. And now let's compare with a 1D case. In 1D, H is just the second derivative. And we know from calculus that for a 1D case, we get a minima if the second derivative is positive, right? And if the second derivative is negative, it's a maxima, right? That's what we learned in possibly in high school or college. But that also matches in the high dimensional case, where in the higher dimension this object is now a matrix, and instead of greater or equal to, it has to be a positive semi-definite, which means that for all vectors x, the x transpose h x must be greater or equal to 0. And we know what is the alternative characterization of this in terms of eigenvalues for h to be positive semi-definite? What happens to the eigenvalues of h? Do you remember?
They're all positive or 0.
They are all greater or equal to 0. Exactly. Right. Okay. Very good. Okay. So now we know some optimization, and we know the first and second order conditions of optimization. So let's look at just an example of this, of a function. And this is going to be a kind of an important function in general. Okay, I think we don't have to do this now. We might do it later. But let's try to now we know the conditions, and now let's try to look at some algorithms for optimization. The first algorithm is going to be gradient descent. So let's look at gradient descent. Okay, what is the idea? We can understand this idea by looking at a 1D case. The idea is that, let's say I have this function, right? And I want to kind of reach this minimum point. This is my optimal. I can look at it and I know this is the optimal, right? And let's say I need to, let's think of yourself as someone who's kind of sitting on this curve, and you're trying to figure out, if you're here, right, which way do you move? If this is your current position, if this is like x0, this is where you currently are, which way do you move to kind of reach the optimal point? Do you move to the right here or to the left here?
All right.
To the right. And the way you can think about that is, you can look at the gradient here, which is the slope here, right? And in this case, right, what is happening to the slope here? Is this increasing slope or decreasing slope?
Decreasing.
Right. It is. So if you think about the derivative of this function, right, the derivative of this function f, right? So when you're at this point, you want to move in this direction, right? So if you look at the derivative points in this way, and you want to move in the direction of the negative of the gradient. And that direction is going to be in this way, right? So what you would do is that you're going to take the new value of x new is going to be x old, and you want to move in the negative direction of the gradient at the old value. Okay, and that's basically the gradient descent rule. And what we do is we add a learning rate here, which means we want to control how fast we move towards it, right? Because now I know that this is my direction of steepest descent. If I move too far, I might actually overshoot and go here, right, on this side. and then I again go back here, and then I keep going here, and then I'm going to keep oscillating, right? And if I move even really farther, I might go from here to a really far place, and then I might go again further, and I might just diverge. So I want to make sure that my learning rate is not too big. But again, what happens if my learning rate is really, really small? What is the problem with that? So
It's
what does
slow.
the learning rate? Yeah, go ahead, Anup.
It's slow.
It's very slow convergence. If my learning rate is tiny, very, very small, I'm possibly quite sure that I can converge, but I'm going to converge really slow, which is also very bad, because really the convergence of these algorithms is time is crucial. So we want to converge at a reasonable rate, because that's why we need to our training converges only when we converge to the minima. So we need to make sure that we choose this learning rate very carefully. Okay. So, all right. Okay, so this is basically our gradient descent algorithm. Uh, and then in general, if you have like some sort of loss function of a weight vector W, then this would look like W new is going to be W old minus a learning rate times the gradient of the function. What's happening? At W old, and you keep doing this until you reach converge to the local minima, right? So this is the gradient descent rule. Typically it's known as GD, right? And let's think a bit about this rule, uh, just to get an intuition of mathematically why this is kind of the correct thing to do, right? So if I think of like, I can think of a parameter xt plus 1 is the time parameter of my value, and then it's xt minus, this is my rule, eta times the gradient at xt, and this iterates for different values of t. That's my basic rule. Okay. uh, and then I can take this on this side, then this becomes kind of like a delta x. So delta x is minus eta delta f of xt, right? And then this is like divided, you can think of t going to from t to t plus 1 is 1, and you can think of this as delta of t, right? And then now you can kind of approximate this as a continuous thing where you have, think of this as dx by dt equal to minus eta del of f at xt. Okay, right? And now what is this? This kind of tells us that the rate of change of x is minus eta times the gradient, right? And in some sense, if you try to solve for this, kind of that would give you kind of a solution for x of t, right? And it's going to be like a exponential decay. That gives you kind of an idea of the convergence property of gradient descent. We'll actually talk more about convergence maybe next class, just going to give you an idea of what to think about here. Let's look at another perspective of this. So we have, so now let's kind of go back to the notion of a directional derivative. So we know that I have the function x, right? Let's say I have x and I move in the direction of alpha of d minus f of x, and I divide by alpha zero, and we know that this is the direction inner product with f of x, right? What does this tell us? This tells us we are trying to find the direction in which to move such that I want to move in a direction. So let's say I have this function f, right? Now this is my function f. Let's say I'm currently here. This is x, and I'm trying to find a direction to move. This could be here or here in this case, but in high dimension it can be many more directions. I want to find a direction in which to move where I can lower my f as much as possible, right? So I want to try such that I can get a value this is much smaller than this value, right? So what direction d can I choose to make this like lowering of f as much as possible? Like what value of d should I choose to minimize this directional derivative? Because if I minimize this, right, if I can make this like as large as possible, then if I make this, so like I want basically f of x, I move in the direction of alpha x plus alpha d, and my hope is that this is going to be much smaller than f of x, which means that I want this to be a negative value. Like how can I, if this is the equation, what value of d should I choose to make this distant this value as negative as possible? Like what would you choose for d here to make this inner product as small as possible?
-1.
Sorry?
Would it be -1?
-1 is a good choice, but if you think of an inner product, so in this case d is the variable, right? But and del of f of x is fixed for the function. Okay, at the given point x, right, at this point the derivative is fixed, and now I want to find a direction that's going to minimize this inner product, right? So inner product, what is the range of values for the inner product? What value of d can I choose to minimize this inner product where this is a constant del of f of x? So if I choose d equal to minus del of f of x, then what do I get? Then this becomes minus del of f of x comma f of x inner product, which is equal to minus x norm square. So this is going to be a very big jump to make this much smaller as possible, which is why this is the direction of maximum descent. And that's why this is the chosen direction of gradient descent. And that's where the rule comes from. So if I now think of my xt, I'm say that I want to make xt plus 1 by moving from xt in the direction of like some parameter alpha times d, and then that is going to be xt minus alpha times del f of xt, and then we call this, we would say this is kind of the learning rate. Okay, so that's that's kind of the origin of the gradient descent algorithm. Okay, questions? Is this making sense? We'll talk a bit more about gradient descent in next class, and we're going to talk a bit about its convergence also. So even if you don't use anything else in optimization, if you only know gradient descent, you can actually build a lot of powerful neural network models just with this learning rule. And this typically for many problems, this suffices. Okay. All right. So let's look at another method, and with that we're going to end it, which is the Newton's method for optimization. So the gradient descent is what we call a first order method. Can anyone tell me why it's called a first order method?
It requires knowledge of the gradient.
Exactly. We only need knowledge of the first order derivative or the gradient. So Newton's method is a second order method. Which means that it requires both the gradient and the Hessian, which is the second order derivative. So we need to compute both the Hessian and the gradient to use Newton's method. Okay, so let's look at how to get the Newton's method. All right. So let's look back at for a function. We know that we have the Taylor expansion, which is x plus, here we have a term delta x transpose the gradient of f, plus we have the second order term delta x transpose, and we have the Hessian. Okay, so now for Newton's method, we know that if I want to optimize f or find a minima, right, my first order condition is that my gradient must vanish, right? So let's set this to 0 and let's work with what else we have. So now we have f of x plus delta x equal to f of x plus this quadratic form. Okay, and now we have this equation here, right? We have this equation here. Let's take the gradient. So let's take a gradient on both sides of this equation. So I'm going to take the gradient here, here, and the gradient of this object, right? So on the left hand side, I have f at x plus delta x. If I take the gradient of that, that becomes delta gradient of f of x plus delta x. And then here I have x plus this is a quadratic form. If I take the gradient of this with respect to delta x, what would I get? We just did this today. The gradient of a quadratic form, what would be the answer?
hx.
Hx, very good. So it's the Hessian times the increment delta x. Okay, so now we have this equation. Okay, now I want to, basically Newton's method says that I want to find an increment delta x such that from x, if I go to x plus delta x, I want my function to be minimum, right? So if I want f of x plus delta x to minimum, what would be the condition for the gradient of f at x plus delta x?
Equal
If I
to
want to equal to 0, exactly. So I want to find a jump such that this quantity becomes 0. So let's equate this equal to 0. And now we have that this is 0 is equal to the gradient del of f of x, and then plus I have the Hessian. And now let's say delta x is a difference between two consecutive x values. So I'm going to call that the x t plus, or let's just use k here. So I'm trying to derive an iterative algorithm. So this is the k plus first. Oh, this is the k plus first value of x minus what? Which x should it be?
k.
xk.
Xk, very good. Okay. All right. So basically, I'm trying to find a rule similar to this rule where I would say that what is the next value of x I need, such that if I keep applying this rule, I would reach a minima after a number of iterations. So now this is my rule here. So I just want to find a expression of xk plus 1 in terms of everything else. Okay, so I can take this to this side, right? And then I get h times this x minus x k is equal to minus the gradient of f of, and this is going to be at x k. Okay, and now h is the Hessian. We know that it is, for the minimum it has to be positive semi-definite, and then it's also symmetric. So if I want to get rid of this h, I need to multiply it by the inverse, and here we're assuming that the inverse exists. So we would get x k plus 1 minus x k is going to be equal to minus the Hessian inverse, right, times the gradient at xk. Right, and this Hessian is also computed at the point xk. And now we finally have our Newton's rule, which is the next value of xk plus 1 is going to be xk minus h inverse times the gradient at xk. And this is called Newton's method. And it is a second order method because we have to compute the Hessian to find this new value of xk plus 1. Okay. So can someone tell me a drawback of Newton's method?
More computationally expensive.
Exactly. It's really computationally expensive. Think about if x was like a 2 or 3 dimensional vector, then probably it's okay. But if you think about a typical problem in a neural network, your dimensionality of x of here in a neural network, x is going to be the parameter space or the weights. You might have millions and billions of weights. So if you have a billion dimensional parameter space, right? If it's like if d is 1 million, then the size of h is going to be d square or 1 million square, and you have to compute that inverse. So that is computationally very expensive, which is why the gradient descent, which is the first order method, is usually much more popular because it doesn't require a second order inverse of a matrix of a second order Hessian matrix. So that's one of the drawbacks of the Newton method, but it actually the benefit, so the negative is expensive, but the positive is actually faster convergence. This is actually going to give you what is known as quadratic convergence. Which is much faster than gradient descent, which only gives you linear convergence. Okay. All right. Any questions on this so far? All right. Okay. We still have a bit more to talk about optimization, so we're going to continue that next class, and after that we'll start backpropagation. But if there are no more questions, I think we can end here today, and that's all for today. So this will be the end of today's class.
Professor, I have a question about the homework.
Yeah, go ahead.
Specifically about the report, because I saw the rubric was had a specific structure that it was talking about, where we have an intro, method, but the actual homework, like, has like all the problems separated out. So is it fine if I like basically like just make the report in the structure where I just like talk about each problem, like, like every code and output is just only shown for each problem?
Yeah, I think that's fine. Yeah, just mention that, and that should be fine. Yeah,
Okay, cool. Thank you.
sounds good. All right. Okay. Any more questions about anything, logistics, assignments, or the lecture? Nope. All right. If no more questions, then that's it. Have a good night, and hopefully I'll see you all in class next week. Thank you.
Thank you.
Okay.
Thank you.
Bye. Thank you.
Thank you. Have a nice weekend.
Thank you.